What we always have from the left side of your screen to the right is a passive sensor for load, weighing models, load cells, or force, also called load cells in English, but they are measuring units. And those sensors are passive. That means we need to have an external voltage to supply the sensor. Internally, you will find a spring body, and if the force sensor is subject of a force introduced into the sensor, we will have some deformation. Strain gauges glued inside will turn that deformation into a change of resistance, and by a special circuit, the so-called Whetstone bridge, invented more than 200 years ago, you can turn that in a little measurable voltage. Well, this voltage is really small. Normally, the supply voltage that you get on the load cell is something like 5 volt. So on a full scale, you get an output signal, typical handling. Next step in our signal chain is the instrument, the signal conditioning. The signal conditioner has 2 jobs to do. First job is to provide the load cell with the required external voltage. And the second thing is to amplify the little signal so that we can use it for a AD conversation, and then we get digital numbers, and then we continue with digital filters, scaling, integration function, and in many cases mathematics as well. The connection between the 2 components is the cable. And the cable is one important thing today, because this is not a single cable that you use to wire your plugs in a house. It is a measurement cable, 6-wired, double shielded, and so on. This is very reliable. The technology is proven, but you do have to do what you are doing there. The next step is the interface. It could be an analog output, 0 to 10 volt, 4 to 20 milliamp, are very common in industry as well today. Also serial interfaces. I always remember the RS488 in the load cell technology, or it could be also a free bus connection. And then it goes out to your data acquisition system, to your PLC, to your control system, or also to SCADA, to the ERP systems in the world. So Martin, what did we change?
Yes, so now we have the smart sensors platform, as I mentioned. And what is a smart sensor? Well, you can see here a smart sensor in this graphical representation. It contains 3 elements. So on the left side, you have the traditional sensing element. That would be the equivalent to your traditional load cell. But what we then do is we integrate the amplifier, we integrate a microprocessor and a communication interface into one single unit. So this single unit comprises everything you need that you have seen also in the previous slide that you have in the traditional measuring chain is reduced to one single unit. And this is a smart sensor. Yeah, next slide.
Well, here you can see a little bit more detailed what we are integrating in our sensor. The sensor, the Whetstone bridge, is untouched. So we use our known reliable sensor and take it to the digital world. Then we have the analog digital conversation. We have a scaling function there. We have some signal conditioning and the output to the ionic master. There is a second red line way. This is the so-called sensor health monitoring, which protects you from sensor failing. More about that later. And you can see right in that slide, there's also a temperature measurement. So smart sensors have one benefit. They give you more information than traditional sensors because the temperatures, additional information is also available with those sensors.
Yes, so what you have seen in the signal chain already is a hint of that there is the possibility to store more data within the sensor. And this is a huge efficiency benefit for smart sensors. There are a couple of things I just want to point out. So first of all, it's an easy setup. What you have seen from the comparison of the traditional measurement chain to a smart sensor means that the cabling is gone. You don't have to have hand wiring going on. You have a plug and measure functionality. The second thing is that all the relevant information for a sensor that you can think of, like the calibration data, the sensor's limits from the data sheet that you would have to look up and see what are the limits of the sensor. All of these sensor-specific data is stored within the sensor's electronics. And additional to that, you get more information. So additional information. You don't only get the measurement signal. For example, if you have a force sensor, you get the force signal, but you get added to that, you get temperature readings, you get information on the runtime of the system, you get the minimum and maximum values, so statistical information of the sensor. And this leads to sensor health monitoring feature we have integrated in our smart sensors, which we will address in the next slide in more in depth. But this feature just should showcase that with more information in the sensor, we can track the health of the sensor. And overall, what you can imagine by looking at the comparison of a traditional measurement chain to a smart sensor, you're reducing components from the traditional measurement chain to a single unit. So you don't have to have the cabinet, you don't need a separate amplifier, and you don't need costly cabling. So there are cost benefits definitely for smart sensors.
And more than that, we can also reach potentially, or in real life today, better accuracy. One example is the temperature. Passive sensors that we build today, they are very precise, but somehow limited in some cases. Temperature effects you can only compensate with a linear function because you use nickel elements to do so. With digital measurements, digital temperature measurements, I'm able to compensate also non-linear effects. We can add a linearization into the sensor, so you can use the calibration sheet that you may have to linearize your sensor and also to come over the tensile compressive sensitivity deviation. And we do not have critical expensive cables for the connection of the sensor to the next stage of the measurement step. And electromagnetic fields become less important because the transmission is digital and really stable against noises. Let's bring that into practical life. What you can see here is a little bit of a look into the HPK development department, and you can see this, the curve that you see, not the flat line, the curve. What you see is the original output or linearity area of U2B is 5K. You can see with 400 ppm, 0.04% maximum linearity error, the sensor is not bad, but there is a linearity error. If I now give in the calibration data that I may have, you can see you get a flat line and the linearization deviation is completely compensated. The only limit is repeatability error of the machine that we use for the calibration and the repeatability error of the sensor itself. Second thing, you may see the arrows that I put into the slide on the right and left-hand side. This is the rated output of the sensor, and it's slightly different for tensile and compressive forces. After the compensation, this is also a flat line, normal tensile compensation sensitivity deviation. Health monitoring is one important thing. As Martin mentioned a second ago, we have introduced not only the sensitivity of the sensor, but also the physical limits of the sensor, maximum torque, overload data, dynamic limits, and they are all stored in the sensor. And what we are doing there is we're comparing the actual force, torque, or load on the sensor with the physical limits of the sensor. And in case that you exceed the limits, especially the dynamic limits, which is not a frequency, but a peak of it, then we give you a warning. And the good thing about that is that we are internally running the system with 40 kilohertz for torque and force. So also fastest peaks, or if you use filter, are detected, and you will get your warning before the sensor fails. That means in overload situation, you get a warning and you can take action before your production stops.
Yes, so now I want to introduce to you the shift in concept of what smart sensors actually bring as a feature, a functionality. And this means that there's a pre-processing going on within the sensor. So having the microprocessors, as I explained before, in the sensor, we have possibilities of doing calculations on the measurement signal. And so you see the three domains we're talking about today is force, torque, and load. And so you can see a couple of the features we have implemented within these smart sensor ranges. So from what you can see is we have digital outputs for all of our sensors from the force, torque, and load domain. We have limit switches integrated. We have peak value detection, but we also have domain-specific algorithms. So for example, for the torque, you have a power calculation. You get additional measurements like the rotational speed, the angle. For load cells, for example, you have weighing technology filters, which are specified or adapted to weighing technology applications. filling algorithms, check weighing algorithms. And for force, especially important, all of the statistical information that you get, like min-max values, all is pre-processed in the sensor. So what you get is results that actually help your process. You don't have to work with a raw data stream, even if that's possible. So with these smart sensors, you can just as well get the measurement signal to your PLC, to your IT system. But the shift in concept here is the smart pre-processing of the measurement signal. And last comment on the sensor health monitoring, what Thomas just talked about, this is integrated in all of our smart sensors. Yes, and now the open question. Smart sensors, so good so far, nice features. Why did we choose for the iOLink interface? And this is the question we want to answer in the next slides. So first of all, what is iOLink? iOLink is a communication protocol. It's designed to let the connection between field devices, that could be sensors, actuators, valves, to be connected to the application level of the PLCs. So that would be the automation level. It's a standardized technology. It's standardized in an IEC norm. And if we look at what actually the iOLink solution is comprised of, we have the iOLink devices. This would, for example, be a load cell with an iOLink interface shown in the picture. Then we have an iOLink master. This is essentially a hub that connects the single iOLink devices. And so one point to mention out here is that the connection between the device and the master is a point-to-point connection. And the third element of the iOLink solution is a so-called IODD, which stands for IO device description. You can just think of it as a device description file similar to a driver, that when you hook up a printer to your computer, you need a driver that interprets the functionality of the printer. Same approach for the iOLink devices. The IODD file describes the functionalities of the sensor for the master and for all the PLC applications to interpret. Lastly, a very big benefit for the iOLink interface is the field bus independence. So down below, you see the most common and standard industrial Ethernet protocols. There are currently iOLink masters available for all common industrial Ethernet protocols. So essentially, this means that you can build up a field level setup of iOLink sensors, and you don't have to bother about the PLC architecture of your machine. You can adapt to it whatever the requirements are. It could be Profinet, it could be EtherCAT, but the field system setup is the same with iOLink. Yes, and in the top right, you can see here a typical system setup. So you have the field devices, you have the masters, and from the master, you go to the PLC, for example, or to engineering tools in the IT level. A very, very important fact of the iOLink solution is that we have a simplification of the signal, cable, and connector variety in the field level. So everybody of you who's been working in the field level, having to connect different types of sensors, different signal types, different connector types, you know that this can be a severe hassle. What you have with iOLink is a standardization. It's the unification of the signal type, iOLink signal transmission, and a unified cabling and connector standard. So what we will show you later in the demo will exemplify this. It will be the same connectors, the same cabling, and the same signal transmission for different sensor domains. And this is a huge change to the traditional way of connecting different types of sensors. Lastly, what I want to point out down below in the left side, you see the growing amount of iOLink device nodes in the field. So this is constantly growing. So the iOLink standard is constantly growing. It started with switching sensors in the automation industry, and now we are introducing sensors for the mechanical sensing domains like force, load, and torque. Yes, and here maybe another just representation of the typical iOLink system setup. So on the left side, you see the iOLink devices, which would be the equivalent to our iOLink sensors. We have the master. So we have the point-to-point connection between the devices and the master. And what we are going to showcase today in our demo setup in a couple of minutes will be, we are using the Ethernet connection from the iOLink master, and we are using engineering tools, or we are logging into the web server of the iOLink master. Typically in applications, in machines, in the automation, what you would do is you have the industrial Ethernet connection going to the PLC.
Yeah, nice questions. How fast can I measure? We are very often asked that. And is iOLink slow? First of all, HBK is using the COM3 standard, which is the fastest iOLink standard so far in the market. Well, looking a little bit more in detail, it starts with the mechanics, and you can never be faster as the mechanics. And this is a question of the resonance frequency. Not the resonance frequency of the sensor on its own, but the resonance frequency of the sensor with all the accessory that you may mount. Additional masses will drop down your resonance frequency. It is really a golden rule of thumb to say you can measure up to 20% of the resonance frequency of your system. So built-in sensor with the whole thing. That's the first gimmick that we have. Internally, the system is running the amplifier for force and torque are running with 40 kilosamples. That means we have 40,000 measurement values per second. Another golden rule of thumb is 1/3 of that is the bandwidth internally. So we have internally a bandwidth of 4 kilohertz, and for the very, very most application, I would say for all applications in the industrial world, this is fair. So 4 kilohertz is something we can do internally, and your limit switches, your digital out, will go with that frequency. Now we have to put out the data via an iOLink master. An iOLink master is something that tells the device, give me the data, and then we talk about cycle time. So the question is, how often can your iOLink master get data from the devices? And this is different from model to model. So this is not an HBK device sensor problem. It is the question of choosing the right fast sensor iOLink master so that we can do. The sensor itself is able to give measurement data package with every 0.9 milliseconds. So more than 1,000 data in 1 second, if you have the right master. And now we can take the other rule of thumb again and say, well, 1/10 of that is the bandwidth that we can realize. So for the measurement data on your output system, not on the limit switches, not on the digital output, on the real data that you give in the master, you can realize a bandwidth of 1/10 with a master able to get that. If you got a slower master, things will change.
Yes, coming to another performance factor, question about signal runtime and the achievable cycle time. So pointing out here from the signal chain, you can see that the signal runtime through the smart sensor is massively influenced by filters. We know this when we look at signal chains. These filters switched off mean that you can detect the fastest signal runtime from a physical impact to the output of the sensor. And for force sensors, for example, we have a 300 microsecond signal runtime. So you can detect the physical impact, and after 300 microseconds, we have detected the max value, the measurement value, whatever you can think of at the sensor's output. So this is a very fast signal runtime for the sensor itself. Now, the big question is, how does it look like between the cyclic data transfer between the iOLink sensor and the iOLink master? And so here are two things to consider. You have the cycle time of the device. So this is the minimal cycle time that the device can achieve. And you have the the master cycle time. So that is the cycle time that the master can achieve. And out of these two, there will be the device master cycle time, which will be established. And typically the master is the bottleneck. So the master is then, for example, if we have a 1 millisecond cycle time that the master can achieve, for the conservative calculation, you can think of the 300 microsecond signal runtime added to the 1 millisecond cycle time. You get 1.3 milliseconds of overall signal runtime from the physical impact until the data is ready in the master for IT and OT level applications.
As a maximum.
As the maximum, yes.
It's maybe faster. It depends on
the master you use. It can be faster or slower.
Okay. Yeah. If you have interest, give us a call. But this technology leaves you to really fast and massive reduction of your costs by the cables that you use, by the speed of setup, which we saw in a second. And it is also a technology that shows more performance than we have today in strain gauge-based measurement chain for the industrial world. For sure, if you use a high-end reference system, it may be even more precise. But in the industrial world, we have a massive advantage. And I think now we're coming over to our live presentation. That means I need to change my workplace and go to the table below. And Martin needs to start up his engineering software so that we can continue.
Yes, so in a second, I will switch to our demo setup. So now you should be able to see our demo setup. So Thomas, explain to us, what do we see here on the table?
Yeah, we have started a while ago with the first ionic sensors, miniature sensors from the as we call them. And now the latest baby in the group is the United 3. This is a flange sensor.
Now it's in the picture, yes.
It's a flange sensor, so we can easily mount it and etc. It's a nice accuracy and very fast. This is the version with 50 kilonewton that I've got in my head. And there is the inline amplifier with the ionic module internally. You can see this is an inline concept, but sensors with really integrated boards are on the way and will be launched very soon. I will connect that now to the Ionic master, and what we've got a model here is from the company IFM, and I simply will connect now that United 3 device master, and Martin will show you screen, which takes a second. We are sorry for that.
So I will switch to the engineering tool we are using for today. So this is just an example. And now what you can see here, Thomas connected the sensor and it has already detected, is reading out basic data. Unity 3A is connected.
What is very, very important, Marta actually could be so kind and go to the raw data. From that second on, direct values measured in Newton are transferred from the sensor to the maps. So you can see there are hexadecimal process data as they call, and you can see they are valid right now. So looks that our measurement is okay. Next step is install the drivers IODD file, and this is very comfortable multi here in this engineering tool.
Yes, so what we do is we just press on search IODD, and you see that we are tracking the internet, logging into the IOLINK database, and it downloaded the IODD file automatically. And what you can see here is now we get more information. So the engineering tool can now interpret the sensor's functionality. And so if I just showcase in a short overview here on the side, you get the different parameters that we can adjust. So for example, filters, zero setting, switching channels, digital output.
No, we don't show them all.
No, that would take a bit too long.
So if you can go to the dispatcher dashboard, and we can show it really measures right now. See now, this is a very low noise amplifier. Please remember all filters are switched out in our situation, and the capacity is 50 kilo. And if I press down a little bit here, you can see I can make real values. Okay, not too much because it's on the table. I don't want to destroy the table. And the output, as mentioned before, this is 50 kilo load cell, so it is very difficult to press the add. All right, that was a force sensor, but we have other domains.
Yes, so we will switch back to the demo setup in a second. So now you can see the desk setup again.
And now we've got another baby that we just launched to the market. This is a PW6D. So this is a laser for kilograms. And also here we have got the inline concept. We call that LCMC, meaning you can digitalize your load cell, most of the beam load cells that we have, I think all of the beam load cells that we have. And I will connect that to the device again. And I think it is not so important that you can see what I will connect. It's more important to see the software right now, that you can see what happens there.
So now you see here, no additional sensor connected. Thomas is connecting the load cell now. And the master has detected the load cell and reads out the basic data. In this case, we have already loaded in the IODD file. So what I can show you here is just an overview of the functionalities also quickly of the IOLINK load cell. So if we go to parameters, what you can see here, digital filtering, we can set up to the 5 stages filtering. We have the switching signals, we have the adjustment. So a teach-in process is possible. Also with this case, running through all the features would take too long, but I think, Thomas, you want to showcase a short demonstration of the measuring.
Yeah.
So
I've got a weight of 100 grams here. You can load cell, you can see 100 grams, so it really measures correctly as well. Now, the important thing is once you have the IODD file and do the setup, it is possible to do all your settings, to do a copy of all your settings in the master. And in case you need to change the sensor, just plug the next one, the measurement goes on. It's really true. And what you have also, which we wanted to show you, it doesn't really matter if you connect a force tooth user or load cell. The doing is always the same. It is always the same cable, it's always the same thing, and the engineering software or in PLC recognizes sensors directly and gives out correct measurement value without any adjustment. That's important. Good. Martin, what's next?
Yes, so now we'll just showcase a very important feature of the IO-Link system. So now what we will do is I'll just switch back quickly to the desk setup. And so with different IO-Link masters, the big word for IO-Link solution is interoperability. So every IO-Link master complies to the standard, meaning that our sensors work with every master. And this is what we will showcase now. So the U93A will be connected.
Shall I do now?
You can connect it to a different master. Yes, that's the pin here.
Yeah.
There it is. So now it's connected. And what I will show you now in a second here is the integrated web server from the Moore master that we have connected. So it has an integrated web server. And now here's the different procedure. We don't have a connection to the internet from the web server of this master, but what I can do is I will just log into this device quickly and get my admin rights. And now I can look in this IODD catalog. With this device, what we can do, we can just upload IODDs. So what I did beforehand, I downloaded an IODD. I will upload it into the device. So now it's uploaded. You can see here in the list, the U93A, which we just used in the IFM, is uploaded. And so this is just the same procedure. What you can see here is we have the IO-Link parameters. And if I collapse all, you see that the master interprets the functionalities of the U93A in the same way as in the engineering tool, which we just showcased. You see the unit conversion, the filtering, the switching channels. So all of the functionality are displayed here and can be set here and parameterized in the web server too. Okay, Thomas, I think you have another...
The reason for that is that all the magic happens inside the sensor. So the engineering software, all the software that you can see on the screen, just is an editor. The magic happens inside of the sensor, nowhere else.
Absolutely.
Okay, we got another short showcase for you to show you the internal 40 kilohertz, and therefore we prepared something we call Google file model and drop-down test. I need to show that here.
So I'm switching back to the test setup. So we have to get it into the picture.
Connected this device here. See that? What I do now is letting this ball falling on a U9C and see what happens there.
So now I have to switch back to our sensor suite, the engineering tool. So let me see which sensor we have connected. So we have a U9C in this drop ball test device. So you see here it's connected. And now we wait what happens when the ball. And so the quick recognition here, if you have detected it, it states the statistics max tracking as 5,800 Newton detected from the drop ball.
But you cannot see anything in the chat, in the line chat. And why is that the case? Because we have used a relatively slow master here with a cycling time of just 2 milliseconds, so quite slow. But internally, we got the 40 kilohertz. So even if the output signal is not going directly to the master in the process data, internally you can sort peak values very, very fast. And by the way, the same thing for the sensor have retard. So also if you have the slowest master on the world, overloaded will be detected, also very fast overload will be detected precisely to enjoy more reliability in your process, and you can take action for something happens. Thank you.
Thanks.
Bye-bye.
Bye.